Hi, everybody. I'm going to talk about how we optimize observing system strategies for tropical cyclone applications. So we have a wide breadth of observations. We take measurements from ships, from aircraft, from satellites. So the question is, how do we combine all these observations in an optimal way so we can do a better job in improving high impact weather events and also save life and properties? So that's what we do. We want quantitative information. We want to evaluate a mix of current and proposed instruments. We also want to optimize data simulation strategies and sampling strategies. We want to do a cost-benefit analysis to improve performance so we can make smart decisions on what satellites or other infrastructures we want to fund next. And we want to also prioritize observing system strategies. We do that in combination and coordination with all the different line offices at NOAA. And this is, for example, one of the things that we look at, trade-offs between small satellites like Cosmic 1 or big satellites so like NPP. So how we do that? I'm going to present here two of the different observing system strategies that we do to quantitate the impact of observing systems. This is an observing system experiments, the first methodology I'm going to talk about. And it's when we deal with the impact of real observations. We have the atmosphere. We sample the atmosphere with observations. We put these observations into a model, and through data simulation, we create an analysis. We do a forecast, and then we verify against the analysis of the next cycle. Based on the impact of a new observing system, we can say, okay, this is a positive impact, or this instrument is doing a neutral negative impact. That works very well when we have the observations. But what happens if someone wants to launch a satellite 10 years from today, and we don't know what's going to be the impact of that instrument? That's why we have observing system simulation experiments, where everything is simulated. In this case, we decide that we know the truth. The truth is a long-term forecast and integration model. From that simulated truth that we call nature run, we simulate observations, and then we put the observations as well into a model. We create an analysis, and we do a forecast. The difference between the OSC from before and the OSSC is that now, because we know what the truth is, we can verify against the nature run. So it's a clear way to measure in a quantitative way the impact of a proposed observing system. As an example, I'm going to show how we apply this for a satellite observing system, Cosmic 2. And just the Cosmic 2 mission, it's a follow-on of the Cosmic 1. The Cosmic 1, at the time we did these OSSCs, it was providing like 1,300 profiles per day, and mostly in polar orbits. So there was the Cosmic 2 mission that was going to follow on to that one. And it was launched in June this year, and it's providing 6,000 profiles a day and an equatorial orbit. So you can see here in cyan, these are the location of the orbits for Cosmic 2 that was recently launched. Just very briefly, for those who are not familiar, this is a cartoon of what a radio occultation, which is a Cosmic 2 satellite type of instrumentation measures. You have a low Earth orbit satellite here that basically tracks the signals that comes from a GPS, or I should say any global navigation satellite system, any transmitter. So when this sets respects to the LEO, you profile the atmosphere. So how did we do OSIS for this? I said that the Cosmic 2 was launched in equatorial orbits, and you can see here the distribution in blue of this equatorial profile, something that we had over the atmosphere. What happened is originally Cosmic 2 was supposed to be in two phases. One equatorial, which is the one that was launched, and the second one was a polar constellation, 6 satellites in polar orbits, and that was done in conjunction, in coordination with Taiwan, and it was a joint decision between the US and Taiwan to move forward with the second constellation, the polar one. So we start doing, basically we're funded by the Weather Service and also by NESDIS and Congress somehow, to start doing, looking at some OSSCs to evaluate what would have been the impact of a polar constellation in addition to the equatorial one. And that's something that you can do with OSSCs. So we run several experiments. One will be the control, which is what's operationally being assimilated. Then we did the Cosmic 2A, which was the first phase of the Cosmic 2. So we had 6 satellites in equatorial orbits, radio occultation type. And the Cosmic 2 was going to be the full constellation that we added the polar and the equatorial together. So we we did some experiments. This is looking at the 500 millibar anomaly correlation in the exotropics. We have here on the left the northern hemisphere exotropics and the southern hemisphere exotropics. And we see the 3 experiments, and this bottom part shows the difference between each of the 2 experiments and the control. Above this line means better, below worse. And you see here the Cosmic 2 was providing kind of a neutral impact, and there was benefit by adding the polar constellation. Similar results by looking at the winds here. There was an increase, a decrease in error mass error for upper level winds. So overall, what we saw is that the global spatial distribution of Cosmic 2 observation is needed in order to prove weather forecasts globally. We just don't need just in the equatorial regions. We need a global constellation. And that's it. Thank you.